Welcome to our after lunch session. Hopefully nobody ate so much that they will go to sleep during Brett's talk. You can see the title of the talk, so I don't need to repeat that. But let me tell you a little bit about Brett. He's won the Engineer of the Year award within the IEEE Reliability Society. He's a full tenured professor at Naval Postgraduate School. I've known Brett for almost 20 years now, and even though I didn't mention that last night when I talked about the relationship between Compass and Siri, Compass is actually how I met Brett. He got his PhD at George Mason University. He went out to Berkeley. He tried to get cars to drive themselves, and maybe he'll talk to you about whether that worked out very well or not. But that was many, many years ago. I consider him a really extremely good friend. He's still with the Naval Postgraduate School. He's in the Arlington, Virginia campus of NPS. He lived in Monterey for many years, and now he's moved to Arlington to help them in that campus right there. And, you know, he's one of those people, kind of like the panel yesterday. He's on the fence, I think. I think he still can't figure out whether he's a formal Methodist or whether he's a testing guy or a reliability guy. He's always somewhere in the middle. But the nice thing about Brett gets it all. He understands everything. So I think this is going to be very fascinating conversation we're going to have today. He's, I think, the last invited speaker that we have in the Siri program. He will be the general chair next year. He's agreed to do that for Siri, and the rumor on the street is maybe next year Siri will not be here, but it might be in California. And having lived in Monterey for all of those years and sailed all the way up and down that area in San Francisco Bay, he knows California pretty much better than anybody. So anyway, Brett, I'll just leave it as that. Is that good enough? Because everybody on the website, I mean, I could go through his whole thing right here. You know, Argonne Labs and this and that. I mean, the one thing you've actually done, Institut National de Recherche sur la Transports et les Sécurité. I mean, see, I can't even read the stuff he's done. Oh, well, that's the reason I can't read it. But I'm trying. But you see, I'm trying to read it. It's off the website. So anyway, welcome, Brett. Thanks.
Thanks, Jeff. Yeah, we've actually known each other for more like 25 years. And I remember being here 20 years ago, giving a presentation on about the same day, same month at Compass, the IEEE conference that was focused on assurance. But we had, you know, the leading folks here on the NIST campus in security, safety, reliability, formal methods. So it's good to be back giving another talk. Yes, and to answer your question, we did get the automated cars to run under fully automatic control, do unassisted lane changes. That was back in '97, and that was at UC Berkeley, and we've seen a resurgence in that interest in automatic control of ground-based vehicles. So hopefully they're not reinventing the wheel, and they're taking some of the lessons we learned about reliability, safety, and security that we learned in that actual demo of that technology. So today I'm going to talk a little bit about formal specification in the context of validation and verification, and how formal methods can be applied at both the validation in the validation of systems as well as in the verification of systems. And this idea of scalability is very important, so I wanted to make sure that I not only talk about the end-to-end process, but the need for scaling. And our first keynote speaker on Tuesday, Dr. Heitmeyer, she talked about size and complexity. I'm not going to talk a lot about size because size, I don't believe, makes a lot of difference in what formal method you apply for V&V. Complexity does, and I'll show you how you can decide what formal method to choose. But I'll have to go fairly quickly. So Some of the things I'm going to talk about, you might want to come up and have a conversation with me offline about the details. I'm not going to talk too much about specification in terms of over and under specification as Dr. Heitmeyer did, but I will mention that as well as a contributing or as a attribute that you need to look at as for what specification language you want to choose. In addition to some of the things that she talked about, I'm going to talk about incremental development, usable formal methods by practitioners, as well as using the formal model or specification that you develop of the requirements as a communication technique or as a medium with your stakeholders, so you make sure that you have the right model that Dr. Heitmeyer talked about, which is really hard to do with some of these monolithic types of models that you develop with some types of formal methods. So with that, let me just get right into the talk. I do have to say that anything I say during this presentation should be attributed to me, not to the U.S. government. I'm representing myself, not my employer. So I don't think we have any members of the press. Yeah, I'm very lucky. I was on Fox News about a month and a half ago, and they tried to set me up, but I just stuck with the program. I didn't let them have me make any statements that would get me fired. So reporters are difficult to work with, especially when it's live broadcast. So there's this perilous journey of software development we're all familiar with. As we know, about somewhere around 85% of the software errors are actually introduced early on at the during the requirements phase. And we know, from about the design time down into reification into code, doing testing, we see less than 25% of the errors, software errors introduced at that time. So what does that mean in terms of verification and validation? That means that unlike the way we've been thinking about verification and validation, where validation is sort of left as an activity towards the very end of the system engineering process to be done, long after we've done a lot of the development, so we actually have code. That's not a winning idea, because then what you're doing is you're falling into that trap of, well, you have errors that are embedded in the system in low-level artifacts that are much more difficult and expensive to take out. So validation really needs to be pushed up to the very earliest points of the development of a system. And we can see verification handles that latter part where we have, from the latter part of requirement specification down to code, but verification requires something that you can execute. Okay, so this is important because there are different efforts out there or initiatives to try to bring validation and verification to the very front end of the software development process, so that we can try to get more of those errors out earlier in the development cycle. There's also this problem of the inadequacy of manual V&V techniques. You may say, why is he talking about this? Nobody uses manual V&V techniques. Well, I work for the U.S. government, and I see it almost on a daily basis where people are writing test cases manually. They don't automatically generate them, and it just blows my mind that they're still doing this. And this is 2013, not 1985. So anyway, manual V&V techniques rely on manual examination of software requirements and design artifacts. Dr. Heitmeyer talked about the fact that humans aren't doing so well at doing very mechanistic things that computers do very well. Manual and tool-based analysis of design and code doesn't go too well, and it's actually not feasible for most of the types of system components, service components, application components that we deal with today. It's ineffective for validating the correctness of the developer's cognitive understanding of the requirements. That's really important, because sometimes we as formal Methodists or testers or reliability engineers, we think we understand the requirements, and we've created a specification, and we're using that specification along with tools, but we really haven't captured the true meaning of what those requirements are. And here's a quick example. I don't have a lot of time. I think I have 40 minutes. But what does it mean by generate a report once every 30 days until the project is complete? So what would happen if we complete the project in 15 days? Do we need to submit it or generate a report? So, I mean, it's very ambiguous. So you need some way of determining what that means. So you have to go back to the stakeholder and iterate and figure that out. Yes?
Right, can I just ask a question? I heard this a long time ago, this is many, many years ago, that human reliability at its very best case is 10 to the negative 3. Meaning, just give you an example. So, like, you have a pilot.
Mm-hmm.
The pilot's got to make some sort of critical decision. The very, very best they'll do is 10 to the minus 3 in terms of getting it. So basically, out of 1,000, they'll get it right 999 times. But the one time, they will completely flunk the test, and whatever happens, happens. So, do you have any? I've never got a reference for that. I've never heard anybody that actually can prove that to me. The human reliability at its very best is 10 to the minus 3.
Actually, there's a good book that was published. Don't ask me the name of the author right now. I think it's Erickson. But there's actually a book on that from the 80s that talks to that. Yep. But there's been a lot of work in human factors, especially in the, that they've actually been able to document that with empirical evidence. And it gets worse because then you have situational awareness and other cognitive factors that come into play, but that's not what my talk's about today. So we can, yeah, but for manual type tasks, it's not such a good thing. But you're talking about in terms of testing, manual testing.
I mean, if you have 1,000 decisions to make,
Yeah.
the very best you'll do, you will never get 1,000 right.
No.
You'll get 190. So manual, B&V or manual certification,
Mm-hmm.
or having assessors come along and look at results that come out of these huge automated processes, try to certify software. If they're always off, or they're or in the very best case, they're only off by 1 in 1,000. It's pretty darn good, right?
Mm.
I'm just curious.
Yeah.
Keep going.
Okay. And then they're inadequate for locating the subtle errors in the complex time constraints software. So timing behavior is something that's really hard to look at, such as, if the pump, this is for an infusion pump, if the pump pressure is turned low and high and then low again, all within 10 milliseconds, the pump should not be high for at least, 20 additional milliseconds. So how do you model that, and what does that really mean? And there are multiple interpretations of that natural language statement. We have different ways of representing that, but we need some way to represent that such that we can show the stakeholder what we think they meant, and validate whether we got it right or not in our specifications. So let's see. So back to here. So software automation, you probably knew this was coming, holds the key to the validation and verification of the behaviors of complex software-intensive systems. I could actually insert in there mission-critical systems, but the idea is they're critical systems in some sense, and that there are certain properties that we want to make sure that actually hold. And it relies on formal specification of system behaviors, and these, as I said, these specifications of behaviors have to match the customer's cognitive understanding of what they want. So some of the factors contributing to specification errors, you've probably seen these. These have been reported in the literature, especially in IEEE transactions on software engineering in several case studies. But incorrect translation of the natural language to formal assertions or whatever type of formal method you're using, incorrect translation of the requirements as understood by the modeler to the natural language, and incorrect cognitive understanding of the requirements as well. So there's an iterative process that has to take place, and I've seen this since I started in my engineering career back in the mid-'80s. I've seen where this iterative process hasn't taken place and systems haven't been used, and the famous Standish reports and the the General Accounting Office, now it's known as the General Accountability Office, reports that say, out of, let's say a sample of 100 systems, only 2 will actually go to full development and be used more than 2 years of government procured systems. And then it's worse. I think it's about 75% of the systems actually never make it past early development stages, and there's a lot of money wasted. But it's often due to requirements errors early on, and that aren't taken care of, and then it becomes too expensive to do anything about those errors. So the process for writing specification is iterative because of human nature. Humans usually write natural language requirements with a specific scenario in mind. So you have to try to figure out what are those scenarios. And you can get those from various sources like concept of operations documents and so on. But and also they encounter ambiguities in the natural language requirement. So writing formal specifications can help us reduce those ambiguities, but it can also lead to writing incorrect specifications of requirements unless you iterate back with the customer. You need to validate and generalize the requirements with a plurality of scenarios, so you can't just use one scenario. So this is kind of counter to the IEEE standards that deal with verification and validation. And you say, what do you mean? Well, as I said earlier, the standards really focus on, the IEEE standards in this area actually focus on doing this as a staged productions where you're doing all the development, but you don't really do the validation and verification till the end of the process. And that's just not a winning idea. So what this diagram is meant to show is a different view, which hopefully will someday be represented in an IEEE standard, where you have closure at these different levels, but as you're building your specification, you're actually going through the validation process, whether it's informal or formal, or hopefully some combination of the two. Okay, so you've got that iterating, but at the same time, as you're moving down into the lower level specification as part of development, you're going to go back and you're going to continue doing that validation process at the same time, as well as you're concurrently doing verification at that point. And hopefully you have a formal method that generates artifacts that can be used both for the verification and validation process, so you don't have an information modeling gap and have to translate the artifacts that you create from the validation process into something that's usable by your tools that you use for verification. And as you can see, the verification process is being done from the product level, which would be something that's actually executable, to the lower level specification. And at the same time you're doing that verification, you're doing validation, and that means interacting with the customer as well. So you're applying both sets of tools, interacting with your stakeholders. Okay. So with formal techniques, though, for doing verification, you have a lot of them to choose from. There is no one-size-fits-all formal verification technique, and I don't think I could use Connie Heitmeyer's technique on some of the systems I work on, not to disparage her approach and her methodologies, but a lot of her work is in traditional what I call classical model checking, and that's great for doing certain things like proving a specific safety property given certain conditions, but there are times when you need to reason across types of scenarios, once again for validation and verification purposes, where model checking just doesn't fit the bill. Theorem proving doesn't necessarily fit the bill, or executable model checking doesn't fit the bill. So we need to select the right tool for the right job in the different phases of software development and for the different context of development. And we need a framework to understand that the effectiveness of different formal methods in different phases of the software development process. And so some of my colleagues back at the Naval Postgraduate School and I have been looking at that. We developed actually a framework to do just that. And we actually have two what we call cuboids, a coverage cuboid and a cost cuboid. A cuboid is just nothing more than a mathematical term for something that is a three-dimensional space, but if you were to draw a solid in that space, it would be rectangular, okay, not a square. So the role of specifications. So we can ask, have we built the right product? And I gave you that example of if the pressure is low, turn low, then high, and then low again, all within 10 milliseconds, and so on. You can see that's a complex timing requirement. So we want to be able to write a formal representation of that, and we want to make sure that we understand the customer's cognitive requirements. So we can think in terms of specification, implementation, and verification. We want to be able to make sure from a validation standpoint that we've actually captured that specification correctly, and when we actually have the lower level objects, that those lower level objects actually map back to the our original requirements. But we also want to do the verification to make sure we have correctness. Did we build the product correctly? So that's, have we built the right product right, is the verification aspect. And the role of validation really is, are we building the right system? And we need some way to do that. So verification and validation are not synonyms as they've often been used in the literature, believe it or not. But I think most people in the community today realize that they are two very different things. So what we came up with is these trade-off cuboids, where we think in terms of implementation, specification, and verification. And the one cuboid focuses in on the cost of V&V, and the other one on coverage, specification coverage. So the specification validation dimension represents the cost, effort, and effectiveness, expressiveness associated with the specification language of whatever given formal method that you're looking at. And it deals with the ease and ability of writing the formal specifications and getting them right. And it's really hard in some formal methods to get it right. I have lots of experience in that area, because I actually even started out my career in theorem proving, and that was one of the most challenging areas to work in. But anyway, getting them to represent the cognitive intent of the human owner has for this requirement is really difficult, and certain formal methods just aren't expressive enough to be able to capture the true meaning of what the stakeholder had in mind. The implementation dimension, this deals with the ease of adapting a given real-life complex program to a specific formal verification and validation technique. And then we have the verification dimension, of course, represents the cost, effort, and expressiveness and coverage of the verification. So the coverage cube, what does it look like? Well, we can see the three axes here. So verification coverage, once again, to what extent can the formal specification be verified? Implementation coverage, how well does the formal specification match the actual code? And then the validation, the specification coverage is validation related, so how well does the how well are the requirements covered? So more is better in this three-dimensional space. So the further out you go on any of these three axes in the space, the better. The cost cube, you need to look at that as well, because here, specification cost, well, this is the cost of writing the specifications. I already said, how easy is it to write them and to get them right. Then you have verification cost. That's the cost of verification, including, how long is it going to take, and cost of modeling, and how easy is it to adapt the model, the program, in order for verification to take place. Because what you'd like to do is, once again, use the same, hopefully be able to use the same specification, formal specification for both verification and validation. So specification coverage really measures the ability to express different classes of system behaviors. So we know that we have logical behavior, as well as we have sequence behavior, so the logical behavior, as you would as the term implies, describes the cause and effect of a computation, and that's typically represented as as functional requirements, whereas sequencing behavior really describes the behaviors that consist of sequences of events, conditions, constraints on data values and timing. So an example of logical behavior would be making sure that this computation, the absolute value of this computation is less than some value. Okay, so that would be logical behavior. An example of sequencing behavior would be once the engine is turned off, the compartment lights must be on until the driver door is open. Okay, so it's a very different type of requirement you're trying to specify. Yes?
That's a quick question, Fred. How about emergent behavior?
How about them?
How about emergent behavior? Is that listed between sequencing behavior and logical emergent behavior?
I wasn't going to talk about emergent. Yeah.
Handle that. I've never understood how they handle it. Or maybe they don't.
They do. They do. Yes.
Oh, sure. Well, yeah. Well, but it might be you can support 40, but sometimes 50 might come along, right? Now what do you do? The emergence is more a function of time and environment. That's my understanding of emergent than constrained up front.
Yeah, emergent can be, for example, and security.
It's a
yeah.
real-time thing.
Security requirements. You can, you can have a system that's safe or secure. And then you have another system that you've shown to be safe and secure. You have the hookup properties, but unfortunately you violate hookup properties that you specify. It's because of the interaction between the two systems that in isolation, independent of one another, they work fine, but when you hook them up, because of the interaction, they actually, yes, they actually show behaviors that you couldn't see in either two. Yeah. No, you can represent those and you can actually reason about them. Yep. That's another talk, so I wasn't going to get into that. We're not going to talk. Yeah. Yeah. But, yeah, emergent properties are a real difficult thing to deal with, so we're not going to try to talk. We're going to stay a little bit simpler here. So, but then we also have, beyond those pure sequencing types of activities, we have timing constraints that describe the timely start and or termination of successful computations at a specific point in time. But then we can also have what are known as time series constraints, and these describe timely execution of a sequence of data values within a specific duration of time. In an example of the latter would be something like whenever the system load exceeds 75% of max load, L must be reduced back to 50% of the max load. Okay. Within 1 minute and must remain at or below 50% of the max load for at least 10 minutes. Now, having someone manually evaluate that statement along with a whole bunch of other statements related to that would be very, very difficult. That's why we have to push it into the automation realm and use formal methods. So, and you can't do that. You can't really. This is where formal methods would be used as opposed to testing, right? But you're still going to do testing because you're going to do that as part of your verification, and you're going to run scenarios that actually run you through different possibilities. And I'll talk just really briefly about assertions, how we've applied assertions to do that. So here's an example of conducting assertion-oriented specification. So what we can do is we can actually start with a high-level requirement. Such as the system shall not exceed 75% of its maximum load capacity at runtime. And then we can reify that or refine that into a lower level requirement, such as the one that I just gave you. I'm not going to repeat that, but there we've worked with the stakeholder and we've learned more about what are the specifics here for that requirement. And so we have these lower level requirements, and what we can then do is we can map those, whether we use assertions or some other formalism, to represent each of those requirements. So we have a one-to-one mapping, and I'll give you the punchline here. The idea is that if we can create a model and in this case using assertions where each requirement maps to one and only one formal specification, it eases the maintenance of that formal model. Okay, so from a scalability standpoint, at least as our model grows, it doesn't become uncontrolled. We actually have some traceability. So if we use assertions and the assertions pop because we've violated some, however the Boolean assertion has been constructed for this particular requirement, we can trace back to that error in the requirements, and then, of course, hopefully we have a traceability requirement into the other artifacts, so we can localize the error and we can fix the requirements error as well as all the how it propagated into the rest of our system development artifacts. So that's where I'm going with this talk. So here's an example of a state chart assertion. And here we map R11 to a formal assertion expressed as a state chart assertion. Now, if this state chart assertion is too complex to easily represent and to explain to someone, then what you would do is you would once again go through this refinement process, and you would break that requirement 1.1 down into 1.1, 1.2, 1.3, or however. 1.1.1 and so on. As many sub-requirements as necessary to make our state chart assertion something that we can communicate, or whatever type of model we have, that we can make this representation something we can communicate back to the stakeholder as part of the validation process. And this is just a larger view of that same figure. Oops. I don't know why it quit on me. It's not supposed to. We have more slides here. Looks like somehow guess we need a formal model checker of this program. Anyway, if logic, behavior, timing constraints. Oh yeah, and for specification, we need to be able to specify both positive behaviors and negative behaviors. So we need a formal specification method that allows us to represent both. And we also need to be able to represent how we can recover from non-nominal conditions of a system. So a negative statement would be, the pump should never operate until at least 2 seconds after a valve shut, which would be a safety requirement. And a positive statement would be something like a pump should remain inactive until at least 2 seconds after a valve shut, which would be more of a design type of decision. So coming back to our coming back up a level, back to trying to decide what formal method to apply for our formal validation verification in that end-to-end type of environment where we have to deal with systems, services, or applications that might have hundreds or thousands or tens of thousands of requirements. We can think about implementation coverage. So this measures the extent a target system may be verified by a formal method. For example, we have the special programming languages tailored specifically for the theorem proving process that does not cover all aspects of the original C program, and hence a low level or low implementation coverage. Dr. Parnas has talked about this extensively. There was an article, I think, in 2010 in IEEE Computer where he went into this in great detail about that semantic gap there between the actual programming language of implementation and the actual formal specification expressiveness and so on. With respect to verification coverage, this measures the thoroughness of the verification by a formal method. For example, whenever a theorem proving process does complete, it provides 100% coverage, which is a good thing, and hence it has a high verification coverage. And specification cost, well, this measures the amount of effort required to express the informal human expectations of formal specifications, validate the resultant formal specifications for correctness, and also it's good for maintaining the resultant formal specifications as the system evolves. So we can actually map theorem proving model checking, executable model checking into these two different cuboids. But we can also think in terms of, well, what happens if, in terms of maintainability of these models or these specifications as they grow larger and larger. So if we have an assertion-oriented specification, we have high-level requirements that are decomposed into more precise requirements that are mapped one-to-one to the formal assertions, which is what I just showed you an example of. And then with model-oriented specifications like we saw on Tuesday during the first keynote address, what you end up with, and I've used those types of methods extensively, is a single monolithic formal model that's really hard to work with, let alone maintain. And that's either for state or algebraic based systems that captures the combined expected behavior described at a lower level specifications of behavior. And it describes these expected behaviors of a conceptualized system from the analyst's understanding of the problem space, but not necessarily that of the stakeholder. And it's just like having an operating system that is, all the functionality of the operating system is together. It's monolithic, as opposed to having a kernel and then having everything else that's not core to management of resources in a computing system outside, like the drivers. So model-oriented specifications get complex and difficult to work with pretty quickly. Requirements are traceable because they are, for assertion-oriented specifications, because they are represented one-to-one by, for example, assertions. And in this case, assertions will act as a watchdog, or as watchdogs for the requirements. Okay, so they're going to pop when they evaluate the false. So a monolithic model is the sum of all concerns on detecting a violation of the formal specification. Is difficult, once again, to trace back to what requirement was it that was represented in that monolithic model that went awry. So we've actually applied this approach of assertion-based modeling to large systems like the ballistic missile defense system, and we were actually able to get incredible productivity improvements. We were actually overnight, we're able to run what they refer to as the Global Integrated Fire Control System software. We were able to do regression testing on that using our assertions that we embedded as part. We specified this formal model. We used the State Rover tool along with this formal method to go back through and search for problems with correctness of the verification, and we actually did validation. And we were able to run that every night. And the developers come back in, and if we found an error, if we found errors, they were able to trace them back and fix them the next day. Usually, they were able to fix them if they were minor or not too difficult to work with. But we also applied this at NASA, their IV&V facility, and they were actually able to do the same type of speed up, and we've actually shown how this can work for even mobile devices, working with mobile devices in that arena, and so smartphones and their apps, and it's been quite successful. So yes, there was a question, or no? Okay, so let me keep rolling here real quick, and we'll get through this. So assertion-oriented specifications have a lower maintenance cost than model-oriented counterpart. When requirements change, once again, there's this ability to adjust the model, which you really don't have with a monolithic model. Okay, so these are some very key things I wanted to impart to you because I've actually experienced this over, I guess it's been 30 years now, on different types of systems, and really the assertion-oriented or assertion-based specification of systems has really proved to be a winner for the many complex critical types of systems that I've worked on. Continuation of, here's some more of advantages, such as assertions can be constructed to represent, like I said, you want to represent the illegal behaviors as well as what we call the good behaviors, the things that we want to have happen. And coming back to the question about emergent properties, I think that, Paul, you followed up on that, but Jeff, that was your original question. You can also specify good emergent properties and those that you want to avoid, such as when we specify security software or system security properties where we, for example, we don't want interference between processes or the ability of somebody to write top secret data down to a lower level in the Bell-LaPadula model, things like that. That would be allowed because of some interaction, emergent behavior that could be created through a covert channel. So it is much easier to trace, also to trace the expected and actual behaviors of the target system to the required behaviors in the requirement space, and formal assertions can be used directly as the input. This is key to the verifiers and the verification dimensions. So you're using one specification to do both validation with the scenarios and verification also with these scenarios with the same assertion, state chart assertion representation. And what we're going to use what we use the scenarios for is for automatic test case generation. So we get away from this manual testing. We actually have, instead of what, I think it was Bob Bender who wrote a classic book on software testing. It's actually about 1,400 pages, and I used to have my students buy that book. And many of my students are military, and they would carry that book to class every day. I was impressed, because that weighed a lot, a 1,400-page book. I don't know why they brought their book to class every day, but anyway. Bob Bender talked about cartoon models and then executable type models that are actually useful for test automation, and that it's a good way of showing or explaining the dichotomy there. And then I think there are probably other advantages, but the last one I want to impress upon you is the conjunction of all the assertions becomes a single formal model of a conceptualized system from the requirement space that becomes validated continuously through that end-to-end proactive process. So it can be used to check for inconsistencies and other gaps in the specifications with the help of computer-aided tools. So let's see, we already covered this. Somehow my slides had a mind of their own. But anyway, if we were to look, we could compare theorem proving, classical model checking, and execution-based model checking. All three of them are very useful. I mean, there are times when you want to use theorem proving, and there are times when you don't, because theorem proving has a high cost, but it does give you great coverage, right? And we can compare these three. We don't have time to go through all the specifics here, but with theorem proving, we have lots of different types of theorem provers we can, and each of these, like ACL2, PL, STEP, PLTL, PVS, whole, and the list goes on, you can actually plot those in those two cuboids, and you can figure out which ones give you the best coverage and which ones give you the best cost, and you do the trade-offs based upon the amount of resources you have and your time, your schedule, budget, and other factors. But the key point here is that existing theorem provers have rather weak specification languages. The behavior expressed in those specifications are not easily visualized, so they're not good for validation. For validation purposes with a customer, you're not going to show a stakeholder a specification in PVS, for example, and they need to create a model to express behavior of a given program using the specification language, and you need human drivers to guide the verification process. So this is in the cost dimension, it's very high. So I don't have time to go through all the different. I'm not going to talk to classical model checking and executable based model checking, but just to show you here we can plot, with theorem proving, we can show that, that cuboid that we get in that, or the actual mapping would be, I'm not going to, yes, I know. I do that in the classroom as well. But anyway, you can see that here coverage is actually quite high here along this, this dimension here, but it's low in specification coverage and in implementation coverage. In terms of cost, specification cost is high, implementation cost is high, and verification cost is high. But you may be willing to go with that cost because it's necessary because of the criticality of the system, and for the type of questions you're trying to answer with the formal method. Okay, we're not going to go through the examples for the other two because I'm going to run out of time. But this computer-aided V&V process, to summarize, should be it should be scalable. It should be of a good, the right cost, the right coverage. And I and my colleagues would advocate the use of computer-aided V&V process that's formal, and it could, we've gone forward in experimentation and actually applied it in the real world using state chart assertions, which are Turing equivalent, and we can actually specify these assertions both as deterministic assertions as well as non-deterministic assertions, and actually you can the beauty here is you can use non-deterministic assertions, and the formalism, the tools can actually work with that non-determinism, but it makes it easier to express the requirements than making them non-deterministic state charts. So it's a beautiful way to go. We believe in using runtime execution monitoring for various reasons, but when you look at those cost and coverage cuboids, use of state chart assertions in conjunction with runtime execution monitoring really pushes you. It keeps costs low and coverage high. And you want to have some sort of scenario-based testing to automate the process. So we've explored this in terms of even not just verification and validation from the developer's perspective, but also that of the independent verification and validation team's perspective. And that latter perspective was actually implemented by the NASA Independent Verification and Validation Facility located in Fairmont, West Virginia. Real quickly, and then I'll wrap this up. We have an IV&V framework as well as one for the developers that incorporates advanced computer-aided validation techniques to the IV&V of software systems. And it captures both the understanding of the problem and the expected behavior of any proposed system for developing the problem via an executable system reference model. Now, I can't go into all the details, but just to let you know, if you're doing IV&V, you could have multiple developers developing pieces of the system, or they're just inversions of the system or program, or the same developer can have different solutions over time. So the goal here is for the IV&V team to develop their own understanding of the requirements, and then to create these state chart assertions, and then test any possible implementation of those the requirements that the developer thinks that the stakeholder has specified, and see if there are any inconsistencies there, and and validation and verification problems. So I'm not going to go through this in detail, but we came up with what's known as a system reference model, which is actually the model of that the verification and validation team that's working independently of the developer actually uses. And then we actually were able to create artifacts that are based upon notations, although they're not semantically always formally defined, but we use ArtUML artifacts because those are good to communicate with the users. But we actually were able to, in this methodology, represent what the system should do, what the system should not do, and how the system should respond under non-nominal circumstances. So in another talk, maybe I'll get invited back to go over the details of this methodology and how it's fared over time. But so far, we've been very successful. I'm not going to fall into the trap that Parnas warns us not to fall into as formal methodologists, to get up and promote what we're doing. He says the formal methods should sell themselves, that we shouldn't, that's his mantra. But if people don't know about them, they're not going to apply them. So it's sort of a catch-22 is what I would say to David Parnas. Let's see, just to wrap it up, let me go to the This end-to-end validation process, what we do is we start by testing individual assertions using scenario-based cases to validate the correctness of the logical and temporal meaning of the assertions. And I talked a little bit about that earlier. And then next we test the assertions using scenario-based test cases subjected to the constraints posed by the objects in that system reference model, conceptual model if you're doing I, V, and V. And then you use an automated tool to exercise all the assertions together to detect any conflicts in the formal specification. And this isn't just smoke and mirrors. We actually have developed tools, plugins to Eclipse, and we use the State Rover, and we've actually implemented both the validation and verification part of this methodology. So hopefully the purpose of this talk was just to, for some of you, to remind you of some of the considerations in choosing formal methods and some of the things that we want to strive for in application of formal methods. For others of you, hopefully this opens new vistas and will interest you in becoming a formal methodologist. Yes, and I can say that I had as a job title at one time at Argonne National Laboratory, my official title there in my position description was Formal Methods Engineer. So that was actually my first job. Yeah, so that was kind of an interesting time. So with that, I'll...
Okay, Brett, that was a fantastic talk. And we can do like one or two questions. I've already given him my couple, and I can always catch him offline. But there must be some questions somewhere in here about, I mean, does this really work? Is it cheap? Is it quick?
Nothing comes for free, but it's actually, yeah, we've actually found it for in terms of dealing with large critical systems. We've found that this assertion, state chart assertion based approach that incorporates executable execution based model checking along with scenario based testing for the automation of testing has actually made what was considered the undoable doable in real systems.
Okay.
So,
questions? Please one more, or I'm going to do one, but I can catch him offline. So, no questions? Can I do one more? Am I allowed?
you're allowed.
Okay. So I love the cuboid idea. I think that's I've not seen this talk. I don't think before.
Probably not.
I've not seen this talk. So I really like the notion of the cuboid. But that's three-dimensional. Now, if I wanted to take that idea and make it maybe four-dimensional or five-dimensional, and I wanted to put things like maybe time in there and maybe money in there, if I could do that, based upon the way you have it right now, so if I could make the cuboid instead of three, make it maybe like 4 or 5, is that someplace maybe you might go in the future with your
Well, actually, the cost cuboid actually takes into consideration time.
Okay, I didn't get that.
Time and dollars, but however you want to represent it, it's the people cost. Like for theorem proving, it's how much time does it take to drive the theorem prover, right? Just if you have a resolution type theorem proving system, you have to define the set of support, and you have to basically guide the theorem prover to finding the proofs. Right? And PVS is very human intensive. There's a lot of human cost there and time to get it right.
I didn't just see that in the cuboid,
Yeah.
so it maybe it's in the presentation.
Well, that was in the, I actually went over that, yep.
Okay, great.
Okay.
Okie dokie, Brett. Thanks, man.
You're welcome.
He's our general chair next year for Siri.
Yeah.
So next year, you can come up with whatever talk you didn't tell us about today, you can tell us about next year.
Yeah, and actually there's a paper in the 2011 in IEEE software that describes this general gives a general overview of what I just talked about today. And there's a paper in IEEE the IEEE Systems Journal that describes the cost and coverage cuboid framework that we came up.
One thing in one of my columns in computer, right, talks maybe a tiny bit about this.
Jeff, when he can't find other people to write, which is pretty often, I'm a frequent contributor to the security column. So You can usually find something from me in that magazine in the security column.
Well written, my column in IEEE Computer Math.
And there's also, not to be self-promoting, but just if you're, we had that the Edward Snowden leaked information about privacy, the violation of privacy. But anyway, it just happens to be coincident that I wrote a paper for this month's, the June issue of IEEE Computer on a cryptographic technique for protecting your data, so you own the, you retain control over who can do what with your data in the cloud. So you might find that to be an interesting article, but totally divorced from this talk. So,
Okay.
so I look forward to seeing you all next year at the
Next year, wherever
Sere 2014.